Physics reaction video number 82. I did a search for wave stuff. Figured maybe at the end of the year we'd find something, but I actually found this channel, and this is from a year ago. It's called the Doppler effect, and it looks like maybe we're going to do some experimental stuff. We'll see. Here we go.
I'm not driving, but I'm going to press this horn and listen to the sound.
Oops. Come on.
Now I'm driving 40 miles per hour, and I'm going to press the horn.
Awesome.
So no matter how fast I'm driving, the sound is exactly the same. But this is not true for a person standing by the road when I pressed the horn. The person will listen a shift sound. One great example of this is when a fire truck is passing by you. This sound shift that you listen is caused by the change of pitches before and after the fire truck passes by you. This relationship between the shift of pitch was explained by the Austrian physicist Christian Doppler. In this lesson, you learn the theory behind the sound shift, and you calculate the frequencies using the Doppler effect formula.
Ooh.
Water and sound waves are mechanical waves. Both need particles in the medium to propagate the energy. We can visualize water waves by observing its ripples and measuring wavelength and period, but it doesn't work the same for sound waves. We can listen sound and sometimes feel its vibrations, but we cannot see how it propagates.
That's a great point. I mean, wavelength in water is
However, we can use the water ripples that we can see and apply the same concept for sound waves to visualize and understand its motion.
I like that.
Let's look at this stationary duck. It makes equally distant circular water ripples. But moving duck, the front ripples are closer together and behind ripples are getting farther apart. This diagram represents a stationary duck on a lake with equally circular ripples. This diagram represents a moving duck on a lake with front ripples closer to each other than the back ripples.
Cool.
Remember, the distance between crests of ripples is the wavelength, and the number of wavelengths per second is the frequency. So we can conclude that a stationary duck will produce equally frequencies, and a moving duck will produce different frequencies depending on the direction of its motion.
So the piece that's implicit there is that the speed of the wave is the same, and it's really hard to see. Oops. Come on.
Sound wave.
There we go. So it's, these diagrams, these videos are really, really great. But the implicit thing I'm talking about, the fact that the wave is actually traveling the same speed in all directions, is hard to show. I mean, you really have to do some video breakdown of this and think about if these stay circular. Let's see, do these stay circular? These actually should stay circular. They don't look circular though. I think they really should. So there might be some. I have to think about that a little bit. But the point is that, so what she's saying here, so we conclude that we'll produce frequencies equally, because she's tying the wavelength differences to frequency differences, which is absolutely right, but it's implicitly built in there that the speed is the same in all directions. Just wanted to point that out.
Waves behave the same way as water waves do. Let us see how it works. This is a stationary sound source produced by a siren.
Ooh.
The siren produces sound waves moving equally to all directions. These blue circles are the crests, and the distance between
Some of them aren't
crests
quite spaced
are
exactly
the
perfectly, but the
wavelengths.
point is, yeah, so it's the
Now, if I
wavelength
place
everywhere.
2 observers on each side of the sound waves,
Yeah,
they are going to listen the same pitch.
yep. Love that.
So this is the sound source, and this is the observer.
Cool.
This is for a stationary sound source. Now let us consider a moving sound source, like a police and ambulance or fire truck sirens. The front waves are closer than the back waves.
So absolutely, what she's saying, the front and back, which is usually all anyone talks about with Doppler, because that's where the calculation is easiest, right? Is that they're jammed together here and they're spaced out further here. But we think about it like as the siren is moving every time it hits a crest, it's like, you know, starting to draw a circle from that moment, right? So if it just emitted a single blast of sound, that would go in a circle. It's just that the source would keep on moving, right? And it would no longer be at the center of the circle. So I actually think these should all be circles. Because the way this is drawn, the wave speed would not be the same in all directions, which of course we do expect it to be. But the interesting point is, all she's likely going to assess and teach is exactly in front and exactly behind. And maybe I'll put a link to the work that I did on trying to calculate it at crazy angles, because it turns out that in drum corps, which is what my kid does all the time, they walk fast enough to affect their own tuning. And so I was trying to figure out just how much that mattered. So maybe I'll put a link into that. But I really love this visual on the front and the back, right? Because, you know, we just get the students to visualize this like, oh, it's scrunched. Oh, it's spread out. Oh, well, then I can remember how the wavelength changes.
We can see the wavelength at the front is smaller than the back.
Yeah, that's great.
We
That's
know
really great.
that for the same speed, frequency is inversely proportional to the wavelength. So the front waves have.
So this is where that implicit stuff I was talking about before, the proportionality constant. Wait, is that the right unit? It's either the speed or 1 over the speed. It must be this, let's see. It must be the speed. The proportionality constant is the speed here.
Higher frequency than the back waves, which has lower frequency. So at the front, we're going to have a higher, louder pitch, and the back a lower pitch.
She said higher
Likewise,
and then lower, but
if
she typed louder.
the sound source is moving.
Actually, that's a really interesting point, right? Because the students sometimes struggle when we ask to describe these sorts of things. They describe the loudness when all we are asking about is the pitch. And so, you know, when we ask people to sing what it sounds like for a car to go by, they tend to get the volume right. Right? It gets louder, and you heard my pitch actually go up like, I got louder and the pitch went up. But that's actually wrong. It's louder and then right. So it's so getting people to really focus on the pitch is hard, because I think it's probably easier to ask questions about loudness. And loudness, of course, is just this 1 over r squared stuff, like how far away is the car.
To the left. The front left waves are closer than the back waves. So the front waves have a higher frequency and the back waves have a lower frequency. Now when a siren of a fire truck approaches the observer, the pitch sounds higher than the normal because the sound waves.
So I just want to pause here for a second, because I'm not sure I'm going to get to the other points in the video, but moving source I think is much easier to describe. Moving source, pictures like these really drive home. Oh, the wavelength gets smaller because it gets crunched. The wavelength gets bigger because it's back. Moving observer, the wavelength is just it's just everybody's the wavelength. And so there you have to like count, well, how many crests did you cross per second? So moving observer is harder. And then of course you get the students who like have heard of or studied some relativity. They're like, oh, it can't possibly matter. And so I want to use the same formula both ways. Well, of course, we all know that when we look at the formulas for Doppler effect, the moving source affects the, let's see, let me say this, frequency is, yeah, moving source affects the numerator, sorry, moving source affects the denominator because that's where lambda is, and moving observer affects the numerator, right? So it's different, different approaches, and yet to the first approximation, they're quite similar. Right, so if you do a Taylor series expansion with the speed of either one of them, you get the same result. So, you know, as long as the things that are moving are much slower than the speed of sound, then yeah, they're both kind of doing the same thing. You can do some quick back of the envelope calculations. But I think that's also interesting that when we're trying to draw these pictures, I think it's these static pictures. This static picture tells the whole story for moving source. But it doesn't tell the whole story for moving observer. But back to the relativity thing, there's actually three things. There's source, observer, and the air, right? So you sort of need to know what all of them are doing because the air is providing, of course, the sound speed. But if the wind is blowing, you also get these effects.
Crests get closer to each other, causing higher frequency.
Nice.
When a fire truck passes and move away, the observer hears a drop in pitch because the wave crests are spread out and the frequency is lower.
Oh, my stuff's in the way.
The observer perceives the frequency as pitch, and the sudden change of pitch is heard as "wee on, wee on."
That was great.
When an observer and a sound source move
Oh, not sure what happened there. Oh, let me pause.
toward each other, the wave speed.
All right, I'm going to pause. Not sure why my computer is being weird, so let me pause this recording for a second. Okay, so seems like I'm having struggles downloading, so I think I'll stop here. So now she's shifting over to both people possibly moving. Oh no, this is still stationary observer, right? So I love a ton of stuff about this. The first 30 seconds of her driving in her car was amazing, right? That in your own car, no matter how fast you're moving, you hear the same pitch. That, I think, is really, really interesting because technically both the source and the observer are moving. They just happen to be moving exactly the same way, and so their effects cancel each other, and you sound exactly the same. So I imagine she's going to get to that eventually because it's really, really subtle, but I think that it drives home this notion that not all the time does moving sound sources create different pitches. It's this interplay between the source, the air, and the observer. So I thought that was really cool. I thought the drawings and the simulations were great, but I do think that I really think everything should have been a circle. Yeah, I'm pretty sure that's probably the better way to think about that. But since most of the time all we care about is forward and backwards, it doesn't matter. So the stuff in front gets crunched, the stuff in back gets spread, and boom, you can figure out the relationship to the frequency. So lots and lots of cool stuff. All right, everybody, well, have a great day, and remember, physics teachers are awesome.